Welcome back to AP Pre-Calculus. Today's lesson is 1.13 and 1.14 together, modeling functions. Okay, so the idea of modeling is also called regression. You may have heard it called line of best fit. It's just here in pre-calc, we're going to do more than just lines. So the idea of modeling is a major component of AP Pre-Calculus. We're going to be using our graphing calculator quite a bit, and then we will be interpreting the stuff that we get that includes context, okay? So get out your calculator, go ahead and take a look at it, all right? So what we want to do to build a regression model is we're going to enter the data. And to do that, we have to make a list, or actually a couple of lists, okay? And to do that, over here, we're going to push this stat button right here. And the very first thing that pops up, and it says edit, right? So when we hit edit, we're going to get this screen right here. So L1 is your first list, L2 is your second list, and you just put in the value, hit enter, it'll go down, hit enter, and you just keep making a list. After you put your last number in, hit enter, and then hit the over arrow right here to get the list 2, and then fill in those lists. So now that we have our lists, we want to make our regression model, okay? And there's quite a few here. You can see linear regression, quadratic regression, cubic regression, quartic regression, and then another linear regression, and then crazy ones down here, logarithmic regression, gross. So what we're gonna, if we ever have to do a linear regression, we actually have two options, 4 and 8. Since some of you might be taking AP Stats at some point, let's go ahead and use 8 when we do a linear regression. That's just because they use that. I don't know why. It's weird, but this is the one they use, okay? So we have all of our stuff in there. We figured out the model we want to use. So we're going to go ahead and put it in our list 1 and list 2. This will be there already, so you won't have to change those. Nothing will be under this regression equation. So we want to put something there. We want this y1 there because we may want to graph this. We may want to see what the graph looks like. And we'll be able to input some values really easy using if we do this. So to do this, there's a couple different ways, but the easiest way is just to push alpha trace. And if you push alpha trace, it'll pull up a box with several y sub numbers, and just choose y sub 1. All right, let's give example 1 a shot. The age in weeks and weight in kilograms of 5 randomly selected babies from a particular pediatrician's office are listed in the table above. A linear regression, y equals a plus bx, can be used to model these data, where y is the predicted weight of a baby in kilograms that is x weeks old. Remember, x is our independent variable and y is our dependent variable. So the independent variable are the weeks in the age in weeks, and the dependent variable is the weight, all right? Because we're expecting as they get older that their weight is going to go up, all right? So we're going to write an equation of this linear model. So go ahead and make your list 1 and list 2. We want T to be in list 1. We want W to be in list 2, okay? After you get that put into your calculator, go back to stat, go over to calc, and you don't have to scroll down to 8. You can just push 8 on your number pad, or you can just scroll down. Either way, that'll bring us to this. Y1 won't be there, so I want you to go ahead and put that there. So arrow down to that until it's highlighted, and then do alpha trace and just put Y1. And then you can go down to calculate, and it should spit out this stuff right here. If R squared and R aren't there, then you just have to turn your diagnostics on. Just Google, how do I turn diagnostics on in a TI-84, and it's really easy. All right, so now we can write our regression model. Y equals, and we're going to look for the A comes first, so we're going to put 3.545 plus, and then B is kind of our slope, if you want to think of it that way, X, okay? All right, let's look at B here. Using the linear model from part A, what is the predicted weight in kilograms of the baby who is 10 weeks old. So all we do is we go up here, put a little 10 in for the x, throw it in our calculator, and boom, we have an answer. But there's an easier way. Remember, we stored our equation under y1. Like, you could actually go and hit the y equals button up there, and you'll see it's there. But what we can do is we can go back to alpha trace, choose y1, put 10 in parentheses, hit equal, it'll do it for us. Not that it was really hard, but it is kind of cool that your calculator will do it for you. Okay? And then C, the weight of a sixth baby is 5.3 kilograms. Using the model from part A, what is the age in weeks? So this is just, we're working backwards. So you got 5.3 for the weight, 3.545 plus 0.185. And then you work backwards to get the answer. But there's also another way to do this. If you did this in Desmos, you can see over here I have a picture of what it looks like in Desmos. And what I did is I added a y equals 5.3 line to my regression model line, and you can see where they intersect. And where they intersect would be the answer that you would get if you did the algebra to figure out x. If you did it on your TI-84, the y1 will already be there, your regression model, because we stored it there. And then in y2, you could put the y equals 5.3, go to the graph, and do an intersect thing, and it'll give you the point there too. And we're looking for the x value of that point. So like I said, you probably have heard of least squares regression, well, maybe not least squares regression line, but you definitely heard of regression models. You should have heard of lines of best fit. Up until this point, we've only really ever done linear regression in Algebra 1 and Algebra 2. But moving on, there's other things. Like, we're going to look at linear models, obviously, but there's also quadratic regression models that we could do, and cubic. There's more, but these are the only three that we'll be doing here in AP Pre-Calc. Okay, so how are we going to know what to do? A lot of times wording of the question will give it to us, but if not, we can look at, remember, if our rates of change are pretty much the same, remember, rates of change is a slope. If they're always pretty close to the same slope, a linear model would be good. If the rates of change are linear, meaning they go up by the same amount every time or go down by the same amount every time, or they're symmetric, or there's a graph that's symmetric with a single max or min, or we're talking about area, all those, I mean, think about area. It's squared, right? And then cubic, context would be volume, right? That would be cubic meters or something like that. Okay, so those are the things, and they're all in that calc part on your calculator. So let's practice using them. All right, here in example 2, we got 3 different scenarios, and we're trying to figure out if we should use a linear, quadratic, or cubic model for this one. So let's look at A. Balloons are filled with water in preparation for an epic water balloon battle. Each water balloon is roughly spherical. The radius of each water balloon is measured relative to the amount of water it holds. Well, we're talking about filling it up with water. That would be a volume question, right? So for volume, we would do cubic. Let's look at B. Totino's pizzas are on sale at the local grocery store. The price of one pizza varies between $1.99 and $2.19 depending on the variety. The total number of Totino's pizzas are counted relative to the total price of the purchase. So for every one pizza you buy, you're going to go up about $2, right? If you buy 3, you go up $6. That is kind of a staying the same. The rate of change stays the same, so that is linear. Okay. C. A sprinkler is placed in a yard to water the grass. The sprinkler rotates in a circular pattern and waters all the grass between the sprinkler head and the furthest distance it reaches. The radius of the circular path is measured relative to the area watered by the sprinkler. Well, I see a word in there that kind of gives this one away. That word area, that would be quadratic. Okay? So that just means we're going to use a different, but we're still going to make a list 1 and list 2. We're still going to go to calculate, but instead of using a line reg, we're going to use a cubic reg or a quad reg, meaning regression. Okay? All right, example 3. It doesn't give us any words that will help us out here, but it does give us a table. Is the change the same? It doesn't look like it. It actually looks like it goes up and then it comes back down. So that doesn't work out so well. By the way, if it goes up and comes back down, that's kind of what you should remember about quadratic, right? So I would say using the quadratic would be the best because our rates go from increasing to decreasing, right? Notice I didn't put INC, I didn't put DEC. Let's go ahead and write things out. They want us to be pretty well spoken on this test. We don't want to do too much shorthand, okay? So, looking at this, where would you guys estimate the vertex to be? Because remember, the vertex in a quadratic is the high point or the low point, and we now call that a relative max or a relative min. And since we're going up and then coming back down, this would be a relative max, okay? And where would that be? It'd have to be around 18. We're not sure if it is 18 because there's a lot of stuff in between these numbers here that it might have gone up a little bit higher, but it's going to be close to 18, okay? All right, so let's go ahead, put these in your calculator, in your list 1 and list 2, then go back to stat, go over to calc, and we're going to use quad reg this time. It's number 5. You can scroll down to 5 or you can just hit 5 on your keypad. Doesn't matter. All right, go ahead and write out your equation. Remember, round to 4 decimal places about. Sounds good? All right, there's our equation for the quad regression model for that data. All right, hopefully you got that. Okay, when we use a model, a regression model based on data that we've collected, that model is a best guess type idea. So we know that it's probably not perfect. So when we make a prediction about something else, about a value that's not in our data, we know that we're probably going to be wrong. And the distance from our prediction to what the actual value of the data is called a residual. All right, so look at that box right here. So a residual, we call it actual value minus the predicted value. Whatever that number is, it is the residual. It could be positive. If your residual is positive, that means your actual was above the predicted. And if it was negative, it means your actual was below the predicted. Okay? And we got to use that kind of context, especially in AP statistics. Like this, a lot of the stuff that we're doing now is big in our AP statistics class. So let's go ahead and look at example 4. This is the same data from an earlier one. So I'll write down the equation that we got earlier. So there's our prediction model that we got earlier, right? And example 4 says, what is the residual of the baby that is 5 weeks old? So here's our baby that's 5 weeks old, and his weight or her weight is 4.4 kilograms. Now, is this the actual weight of the baby, or is this her predicted weight? Well, this is the actual weight, right? So we're going to put 4.4 here. I want the predicted value. So for the predicted, we have to come back over here. And for x, we're going to put in a 5. Or you can do alpha trace, and then in parentheses, put in 5, and see what that comes up to. So if you did the math, you should have come up with 4.47. So We think the baby's supposed to be 4.47 kilograms. It was only 4.4. So I'm expecting to have a residual that's negative because it's smaller than what I thought it was. So we come over here, we do actual minus predicted, and I get a negative 0.07 kilograms, right? So what does that mean? So we had a predicted value that was over what we actually saw. So we would write out that our predicted value was an overestimate. And that concludes today's lesson.